Okay, thanks, Stefan. So I'm going to talk a little bit about our new work with Armin Baumeister. And so what is this about? The idea behind this project is, so can we set up an experiment such that certain observations can be termed incompatible with any explanation or description coming from any theory that assumes what I call a fixed causal relations. And what would be the physical interpretation of it? Now, by fixed causal relations, what I mean, there are different ways. If I am to put a little bit of ontology on top of it, I think people call it fixed background or static spacetime. I'll also refer to it, all of these interchangeably. So the first thing I want to do is actually, what is this property? I want to phrase it in a device-independent way. That means I want to pinpoint exactly what is this property as a constraint that I will, as a decomposition of probabilities that of possible events in agents in distant locations, right? And that I call static spacetime, and that will be the partially ordered correlations. The second thing, I will go directly to the results. I will present these Bell tests for this. And finally, I'll go to the third part, which is the physical interpretation a little bit of this. So the first two are just mathematics. The maybe important part is the third one, the relativistic discussion. And I will end up with conclusions and open questions. So going to the first one, what is a static spacetime in a device-independent approach? So two events, let's say, can have possibly, I cannot move much, huh? Can have possibly two. They can be either time-like or space-like, and they can be time-like, for example, A before B or B before A, right? And when they are space-like, actually these two decompositions hold simultaneously, which means I'll just throw away some of the dependencies to make them look the same. So how does a static spacetime, how does it look as a decomposition, as a constraint? That would look like this, right? So I have one case where A is before B. You see here the output of A depends only on its input and not on anything else. And here also, the B is before A, so it only depends on its input, like here. And has been studied, I think, to my best of knowledge, 2012 was the first time for this. We're gonna do the very general decomposition we are studying in this. I'm not gonna go through the details of what this is, but you can just see the figures and maybe have a way. So what are the Bell tests? So the question is, how do we certify that a certain probability distribution cannot have some decomposition, right? So these are some tools that we already have from quantum information and from quantum foundations, right? So we find, I think this went bananas. Okay, sorry for that. Right, so we find the facets, namely a set of linear inequalities, such that if any of them is violated, we know that a certain probability cannot have this decomposition. Right, and how do we find the facets of this partially ordered polytope? Actually, we reduce it to another problem, and we harvest the results from there. Just a few comments on that. This problem was studied by theoretical computer science in the beginning of 80s, more or less. It's called the acyclic subgraph problem, and I'm not going to go into details, but it's interesting actually that it has been studied in a completely different context. So actually we can harvest all the results from there as soon as we reduce the problem, which we do. So what are the Bell tests? So we're gonna actually, there is a very natural way of phrasing these games, right? These facets of the polytope, if you want. And we are gonna encapsulate or encode this into what we call the Bell test graphs, right? Let me read a bit this, and I hope it will become clear. So let's say we have n parties, and we have one of these Bell test graphs. That is some set D with some vertices V, K, and some edges, EK. So the game is as follows, right? A referee picks at random an edge from this Bell test graph, right? An edge defines a sender and a receiver, and some random bit B, 0, 1, right? Then the referee announces who is the sender and who is the receiver to every party, right? And distributes B only to the party S, to the sender, right? And the parties win this game whenever the output of the receiver equals the bit that was distributed to the sender, right? Now, as I said, now this doesn't hold for any graph. The ones that certify as Bell tests, so the ones that certify for Bell test are very specific topologies, are very specific directed graphs. And they have, like, in the literature, there is at least 8 families of different, very interesting directed graphs that can certify as Bell tests for this one. I'm going to present, I don't have time, so I will go only through one, the cycle graph. And maybe I can also run through an example to see how does this work. So let's say that we have 3 parties, and they are wondering whether they're incompatible with the assumption, whether their observations are incompatible with the notion of a static spacetime, right? Right. And they will play this, what we call for k equals 2, a 2-cycle graph, right? So how does that? I will just read from here, right? So a referee picks at random an edge from this graph here, right? And a bit. That would be, for example, let's say in this first round, it picks the edge A to B and picks the bit B equals 0, right? That means that, and continue, then the referee announces that to all parties. That means this is the input to all parties, and B is the extra input to the sender, which is Alice here, right? Then the parties win the game whenever the output of the receiver equals the bit that was distributed to the sender. So the receiver is B here, and if the output is 0, same with B, then they win. And so on and so forth. I can run a second round here also. Let's say that they chose the other edge. The referee picks at random an edge. Let's say that it picks the other from B to A. And a random bit, it picks B equals 1 for this round, right? Again, B is the receiver, the sender, sorry. Therefore, it gets also the information for the bit. The rest of the parties only get the information who is the sender, who is the receiver. And they win this round if the output of the receiver, which is Alice in this round, equals the bit B, which is 1. And so on and so forth. And at some point when they have enough statistics, they say, okay, are we incompatible with or is it inconclusive, let's say, like the test. So if they find out that the probability of winning this game is more than 3 over 4, then they have certified that they're incompatible with the assumption of static spacetime here, right? And this you can generalize for any k, actually. So this is the general formula, and this for k equals 2 comes to this. And let me say that indeed exactly this game, the bound is violated by the 4-party unitary quantum switch process. Right. So there are, as I said, there are many families of these Bell test graphs, one of which is the cycle graph. Another interesting is the Möbius graph. We have analyzed 3 in the paper, but as I said, there are around 8 very interesting, which we don't see actually what are their components. I mean, why the new thing that these graphs introduce is, for example, non-planarity. Actually, the fact that you cannot draw this graph in 2D without edges crossing, right? This is the new that this Möbius graph adds, which doesn't have the cycle graph. But it's, yeah. So that's for the Bell tests, right? What about the violation in the process matrix formalism? Let me quickly just say that we show that we can violate them for any finite number of parties. And the processes that we show that can violate them, they have the following properties. They're classical and deterministic, and they always produce causal correlations. This will be important for the physical discussion later. Let me go to the perhaps more interesting, the physical part. How do we interpret all this mathematics, right? So we want to exploit these Bell games to make a distinction between special and general relativity, right? And how do we do that? Yeah, in essence, these Bell games, what they tell you is that if you have, if your events are partially ordered, then you have certain limitations on the correlations that you can observe, right? So the definition of what an event is very important and crucial to the physical interpretation that you want to have. So in order to make the physical distinction that we wish to make, which is distinguish between special and general relativity, we use the accepted notion of event, which is the crossing of world lengths. Right, so let's see the setup. What do we have here? We have Alice, Bob, and Charlie in this, space-like surface, and we have many referees. Let's see what they do. So R0 is the one that carries the inputs to the parties. For example, some encrypted light signals. So as soon as R0 meets here with Alice, gives her the input, and so on and so forth. Then we have all the others, let's say they travel close to the speed of light, and make sure that the outputs of the parties are timely produced, right? Because you see here, when rho 1 meets with rho A, this region ends in some sense, right? So these are some causal diamonds, right? That they are the intersection of the future light cone of this point and the past light cone of this point, and so on and so forth. And each event for each party happens within these regions. And by definition, actually by construction, the way that we have made this scenario, the correlation of these three events, one for Alice, one for Bob, and one for Charlie, they are partially ordered, right? By definition, so no inequality can be violated in this scenario. What about GR? So the Bell games presented here are won with classical and deterministic processes that produce always causal correlations. That suggests, perhaps, we haven't done this calculation, that's why I'm speculatively phrasing this, maybe one within general relativity, and likely not with something very exotic, let's say, right? With globally hyperbolic spacetimes, hopefully. We don't need something exotic here, right? For example, we could play in this scenario that I presented, we could play this two-cycle game, right? Alice, as soon as she gets her inputs here, right, and knows whether it's going to be Bob that, sorry for this. So for example, Alice, when she receives from R0 the inputs here, it's going to be either B that has to signal something to C, or C that has to signal something to B. If it's the latter, C has to signal something to B, then Alice may alter the space-time structure within her future light cone, right? Depending on the announced edge that she receives in this region, she could displace a heavy mass, let's say, right? That will invert, compared to the relativistic scenario, the causal relations between these space-time regions, allowing the transmission of signals from that region to this region. And if the probability is more than 3/4 in this game, they have certified their inconsistency with a static spacetime and therefore with special relativity, right? So for example, this would exclude any possible explanation or description coming from special relativity. So let me recap a bit what I said. The point that I wanted to make for this, the whole project was whether we can set up an experiment such that certain observations can be termed incompatible with any description or explanation coming from any theory that assumes fixed causal relations. Fixed background, static spacetime, all these are the same, right? And what would be the physical interpretation, right? I pinpointed this property in a device-independent way. We sort of solved this problem and presented you some of the Bell tests here, and a little bit argued about hand-wavingly about the interpretation and how we can make it happen. And I have many open questions, but I only will phrase one. So the detection of this dynamical causal structure, right? So if we see a violation, can be understood as the detection of curvature change, right? In the GR language. So if we were to see violation of this, we can interpret it in GR as saying like we have seen the curvature change in a spacetime manifold. So the question is, to what extent can these games detect gravitational waves, for example, or and what is the precise general relativistic description of these objects that violate these inequalities, right? And I think that's that. Thank you.